This video is for the purposes of showing you a very quick demonstration of the Smash software from Dolphin Integration. The first thing we'll do is go on to the module box on e-learning and download the design files for the first design, which is featured in the notes. So we've got a course documents and workshop, and then if you scroll down to a few items down the list until you get to the introduction to the Smash simulator, which is here. As I mentioned in the lecture, there's a PDF file which is a PowerPoint presentation showing you the basic steps, which we're pretty much going to follow in this video. But also there's the quick guide files, which is the second item, the zip file. If you click on that, it will open up the archive, and we need to extract the files in that archive, which are shown here, into a folder. So I'm going to do that now onto my my documents area, and I'm going to create a new folder in my Smash projects called the name of this folder will be First Design Video. So make that folder and extract the files into there. So we have a number of files, 11 files, which are all the Verilog Ems files, and also the top level design file, which I'll show you shortly. The other thing that is worthwhile having open is the Verilog Ems handout, which I've given you, and that was in the course documents lecture material. And the only reason to have this handout open is so that you can see the circuit diagram of the first design, which is in this handout. So I'm just going to open that in the e-learning so we can see what the diagram looks like. And that diagram is a few pages into the handout, after some of the previous slides covering the basics of Verilog Ems, and it's this page here. So this is the first design circuit, and as you can see, it's made up of a number of analog components and also some digital components, and a mixed signal component, which is the comparator. I'm not going to explain all of these components in this video. These will be covered in the lecture in due course. The other thing we need to do is, I want to show you where you can find the software, because you can download the software onto your own Windows computer, or indeed you can run it in the lab. So I'm just going to go to a new tab and type in the Google Dolphin Integration Smash, and it usually comes up with the download, which is the second item here. Dolphin Integration is the name of the company, and Smash is the name of the software. So if you click on the first link, it takes you to this page when it loads. This is the Dolphin Integration download page, and what you would need to download would be the well, you download one file essentially, and it contains these three packages. The one that we are really interested in is the Smash software, and this is contained in the Windows Auto Extracting installer, which is the one that I usually download is the second one, and it runs on Windows platforms on both 32-bit and 64-bit. When you click on download, it takes you to a form that you have to put in some details. What's very important is the host ID is the last thing, because the license that you get, which is a 6-month license, has the host ID embedded in it. So to find out what your host ID is, you go to your Start button in Windows. I think this is how you do it in Windows 7. And you go to Accessories and the command prompt, which opens up a command window, and if you type in get MAC, it will give you the physical addresses of the network card in your PC, and that should be what you need for your host ID. So it's taking its time over this, but normally it comes up pretty quickly with a list of physical addresses in this little window, and you need to make a note of that and copy it into this host ID field. It also, on the web page, it also has some information about how to get that physical address. Actually, it's exactly the same as what I've just said, get MAC. I don't know why it's taking so long. Ah, there it is, right. So the MAC address is actually the first one in that list. In fact, I think probably any of those would do, but that's what you need there. And then when you submit that, you'll get an email, and that email will take you to a download site where you will download the software, which you then install. The email contains the license, and you then set up the license in the software. So I'll show you quickly how to do that as well. Just close that tab. So we've downloaded the files from e-learning, we've got the presentation open, just minimize that, and now we'll start the software. So it's basically start programs. Now in the lab it'll be different. The software will be inside of the electrical and physics applications, but if you've installed this on your own machine, you'll see it creates a group called Dolphin Solutions, and in there are the four programs actually. There is a schematic capture tool, but to be honest, it isn't a particularly friendly tool, and it's very limited. In fact, it's more limited than Smash, which means that the design that you can create with SLED is smaller than what you could create if you just created it in text form. So there's no point in using SLED really. So we just start Smash. It's version 6.6, and this will bring up the Dolphin integration Smash software. So just looking at the circuit while we're waiting for that to happen. All of the files in the design are either Verilog, so they're digital, so the components on the right of the dotted line are digital, so they'll be V files, and the components on the left, and including the comparator, will be VAMS files, which are Verilog Ems standard extension. All of these files need to be in the folder of your project, and you'll notice when we open the top level file, which describes this circuit, which is a kind of test bench, that is those are included in the source using the include directive. Okay, so Smash, I believe, has just opened up. Here it is. So it usually prompts you to set up the licenses, but I'll just show you how you do that. You can also close the welcome screen, although there is some information in there about help for files and examples. If you go to the edit preferences in the main menu, first of all, if you've just installed it and you want to set up the license, then it brings up the preferences dialog box, and the licensing tool is down here, and basically you add a local license. So you have to find the file which is downloaded in the email. It's called smashlicense.dat, and it's actually in a zip file, so you have to extract it first. Then you add the local, and it will show this feature in your license, Smash Discovery, which is this evaluation version, and it's 164 days now, because I think I've had it on the system for 2 or 3 days. Now the only difference that makes in reality is that it gets rid of some nag screens when you run the software, when you run the compilation and simulation. You can still use the software without the license, but you just have to click on a few windows to get to the point where you can see the results. While we're in this preferences dialog, you can also change the wave window appearance, which is quite useful for printing waveforms out into a Word document, and there's also other things. The editor can also be customized, The font is, I'll change the font a bit later, but it's Courier, which isn't the best font, to be honest, for your HDL, but we'll come back to that in a moment. Now, first thing I'm going to do is I'm going to go to the File menu and open the file, which is the file for the top level. So I need to go to my Smash Projects and First Design video, because this is where that file is. The file is called a Smash Netlist, and its extension is NSX. Okay, so what this is, it's a general netlist file, which is the top level of the design, and it contains the effectively the diagram, which you can see in the handout. It's a description of this entire diagram. This is the NSX file. So I'm going to actually change the font now, because I think Courier is not particularly the best font to use. So I'm just going to go to the editor and change the font to Calibri. I think is probably a good one, once it finds the necessary file. And maybe make the font a bit bigger, although you can actually do that quite easily by just using the mouse wheel. You can zoom in and out. So moving up the fonts until I get the Calibri, which I think is a reasonably good one for HDL type work. So I'm just going to close that now, apply that, and OK it. And it may be that we need to reopen this file, so I'll just close it and open it again. Okay, so this is the Calibri font. Now what you can do, it's quite small, but you can actually just use the mouse wheel and the control key to zoom in and out, so it's quite useful to be able to do that. So this is the NSX file, and this is the top level of the design, and basically before you run Smash you need to have this file already created. The first line in the file is highlighted in blue, reverse video, and this tells the system what the language is, because you can have multiple sections in this file, this netlist, with different HDL languages, from Spice to VHDL to Smash's own language, which is ABCD. So because we're using Verilog, you need this line at the top of the file. That's always got to be there. Then we have a number of include directives. The first two are always required because they contain the definitions of the disciplines that we were talking about in the lecture, such as electrical, which also refers to the natures, and all the other disciplines that Verilog Ems supports. There is another file called constants.vams, and this file contains a list of physical constants like Boltzmann's constant, the charge on an electron, and so on. And these are all in that file as well, and also some mathematical constants like pi and so on. These are all defined in those files, and you might see some examples of where we use them. Those files are generally available in every project. And then after that we have all of the include files for this particular design. So starting with passives, the passives file will contain the definitions of the resistor and the capacitor, and possibly inductors, any other components that might be in there. They're all in the same file. That's a Verilog Ems description. Then I have some Verilog files. These are the digital components, the DFF, the reset generator, and the clock, which you can see over on the right hand side of the circuit. Then we have the VAMS Verilog Ems files for the gain amplifier, the comparator, the sine wave source, and the DC source. These are all analog, and well, one of them is a mixed signal. This is the comparator, and these are the components on the left hand side of the circuit that you can see on the screen there. Timescale, you normally need a timescale in these simulations, but remember this is mainly for the digital models. Sometimes you can use that in the analog models as well. And then you go into the module itself, which is called First Design. It's a test bench in effect, so it doesn't have any inputs or outputs. It just has declarations of electrical terminals. That's the first set of declarations. These are the terminals in the circuit, like TREF2, TA, TN, etc. Ground is also an electrical terminal, and because ground is a special one, you have to qualify it with the word ground on that line that you can see there. Then the digital signals are defined, declared. These are all to do with the digital components. And then we have a netlist, effectively, of components in the same manner that you create a Verilog netlist. In Verilog EMS is no different. The only thing is that some of the components are analog components. So for example, the sine wave source has an amplitude parameter, set that to 1 volt, a frequency parameter, set that to 1 megahertz. Its positive terminal is on T-in and its negative terminal is on ground. It's quite useful, this editor, because notice how it highlights all the occurrences of the same signal. So the this is this sine wave source over here, and the resistors there are shown, two 1K resistors, and the connections. The amplifier has a gain of 10, and that amplifies the voltage coming from the sine wave, which is a 1 volt peak signal. So we'll see that in the simulation. The comparator, it's a simple behavioural model of a comparator. It doesn't have any transistors or anything in it, but it models the behaviour of the comparator. It has a hysteresis of 0.1 volt and also a delay of 10 nanoseconds, and that's connected up to the analog inputs are on P and N, and the digital output is on comp. So this is really a kind of analog to digital converter. Then you've got your digital components down at the bottom of there. It's worth bearing in mind that this test module doesn't have a stop command anywhere. You can include a stop command because it's part of Verilog EMS, but this one doesn't, and that means that you have to think about how long you want to run the simulation sort of before you run it, and that really depends on how many cycles of the sine wave we want to see in the simulation. The clock has a default frequency. I haven't overridden the clock, so we'll see what that is, but the sine wave has a frequency of 1 megahertz, so we're going to run for a few microseconds probably when we run the simulation. So that's the NSX file, and you need, as I say, you need to create this first before you actually open it in Smash. So I'm just going to close that file. When I say open it, I mean you load it in. All we're doing at the moment is we're editing the file. We haven't actually yet opened the design. So now close that file and go back to the main Smash window, and then to open the design you click on the open and load circuit from the controller netlist files. This is this second tool button along from the left, which I think you can also get that from open circuit. So to distinguish open circuit from open is just opening a file to edit. Open circuit means to actually load the circuit into the Smash system. So I'm going to click on the NSX file now and open the design. And it's at this point that it compiles the design. It also creates a file called a .pat file, which is a command file, and that has the same name as the NSX, but it has the extension pat. And that the purpose of that is to save the commands to the simulator, and also the setup for the waveforms and everything gets stored in the pat file. And you must remember to save that file as you go through. So it now presents you with this window which asks you to set the top level unit, and it's showing me that I have a Verilog a work library within the Verilog area, and in there I've got all these design units which have been identified. Obviously these are the ones in the design, and the top level is actually the one called first design. And what this will do when I OK this, it will actually add this line into the pattern control file. So you can see that happen when I click on OK. And it's saying, okay, what it's saying now is it's changing this file, so do you want to reload that? And the answer is yes. So basically always answer yes at that point, because it reloads this pattern file with the elaborate command in it, which basically identifies the top level of the design. And while once you've done that, you'll notice this green scroll bar down the right. This is now compiling the files in the design and loading it in. If there are any syntax errors in the design, it will actually report them at this point, and you have to put them right before you attempt to reload the design. Looking now, once the design is loaded, we have a kind of a hierarchy browser which shows the structure of the circuit, with first design at the top, and below that you have the signals which you can below that you have the signals which are available at that point in the design. So as I move around from one part of the design to another, it shows you the signals that you can access. So for example, the amplifier has an analog input, and it has an analog output. These little buttons here in this panel show the filters that you can apply. If we look at the clock, that one has a digital output, which is actually a reg type output port. That's the clock output of this clock generator, and the comparator, which has a mixture of analog inputs and a digital output. So if we leave it at the top level for the time being, it means we can add the signals from here into the waveform when it appears. So this is kind of like an Explorer tab once the design's loaded. Behind that you can see the Files tab, and this shows all of the files in the design, and also the circuit load, which is this report file, which basically just gives you some information about the design that you're loading, and the software version that's running, and it tells you a bit about the number of analog elements in your design and the number of logic elements, and it's this information that it uses to ensure that you're within the limits of this version. If you go too high on some of these numbers, it will actually just not, it won't allow you to simulate it. You can also just double click on any of the files and find your way around the design. So for example, if you wanted to look at the clock generator, you can see here that the clock generator has a period of 100 nanoseconds with a duty cycle of 0.5, so it's a 10 megahertz clock. If we look at the sine wave source is described using an analog process, an analog block, which creates a voltage between the P and the N terminal, which is basically defined by the equation of a sine wave. And that equation actually references pi, which is included in the constants.fams include file. It also references absolute time, which is actually the real value of time during the simulation, because that's what you need in this equation, obviously, to give the instantaneous amplitude. So that's the sine wave. We're not going to spend time looking at every single part of the design. The next thing to do then is to go to the analysis command to set up the kind of analysis that you want to do, and most often it's transient analysis. So you select analysis transient parameters, and you need to do this to set up the parameters of the simulation. Now this box comes up, and essentially you don't need to worry about the advanced parameters usually, but occasionally you might need to click on advanced parameters, and it's possible that you might have to change some of these other parameters in this advanced section. Normally you would leave these alone, but sometimes it's necessary to alter them. The simulator is quite sophisticated. It kind of tries to optimize all of these for the simulation, so normally you don't need to change them, but just be aware that they are there. The time that we're going to simulate for, I'm going to simulate for 5 microseconds, and that will give 5 periods of the sine wave and also about 50 clock cycles, because the clock is 10 megahertz. The print step we can leave that as it is, but sometimes you do need to alter that, because if that's too small it makes the simulation take quite a long time to run. Just bearing in mind about a design, if a design has a stop command in it, then it's worthwhile figuring out when exactly the stop command will be executed, and that time is usually what you'd want to put into here, at least that time. You need to run to that time, because the stop command will stop the simulator, but if you've entered a time in here that is past that, then you will be able to run past the stop command up until the end time if you want to. Otherwise, if this time is lower than the point in time that the stop command occurs, it will stop anyway at this time, and then you can run past that to the stop command. So in either way you can run to the larger of the two times, as it were. So now that we've got this set up, we may as well click on Run to run the simulation, and it will save the information about the runtime and so on in the pattern file. Now what I do now usually is I don't use this this box here. I usually just close this box, and what we can see now is the waveform window, and a message has come up to say the simulation is finished. So there are no traces detected for simulation. Please select an element to simulate or close the pane. If we look at the pattern file, it's added some information now. Make sure that that file is saved. This is telling you about the basic simulation settings, and this is needed for the project. If we go back to the transient window, we can add signals from the circuit. So we're now looking at the circuit again, and we can add the digital signals. Well, we can start off by adding the analog signals. So we look at the diagram. T-in is the sine wave. So if we right click on T-in and trace and transient, it'll add T-in there, but you won't see a waveform, because similar to ISE and ISIM, it doesn't save the waveforms. You have to run the simulation again. So if we run the simulation, it should update the waveform and show us the waveform for T-in. So there's the sine wave. It's a nice smooth waveform. The simulation runs pretty quickly. You can see it's got an amplitude of 1 volt, and that runs quite well. And you can see you've got 5 cycles there. So now I'm going to add the output of the amplifier, which is TA. So select TA, trace and transient. Again, there's no waveform there, so we would need to rerun. If we rerun again, it will hopefully show us both waveforms. Yeah, there's TA. And TA is 10 times T-in. We can actually superimpose TA over T-in by just dragging it up like that, and that's also quite useful to show the effect of the gain of the amplifier. The colours change also as you move the cursor over the waveform. It highlights it in the waveform window, which I think is really useful. Now we're going to go and add Tref, which is a DC level. So Tref is this signal here, and this is, I'm going to also put this into the same area as the other two. Just run the simulation again, and you can now see the reference voltage there is at 6 volts, and that's being compared with TA. So Tref and TA are actually going into the comparator. If we just go back to the pattern file, we need to make sure that we save the pattern file, and it updates it with the trace command, which is basically controlling this display. So it's important to have that. And then I think the next signal is really the comparator output that we need to look at. Now this is a digital signal, so it's got a different symbol. So add that to the trace, and we don't want to put that in here. In fact, it won't let us because it's digital. We want it to be separate, and if we run that again, the running of the simulation is actually done with the run button, which is in the toolbar at the top here, the little play button, and now you can see the comparator is operating correctly, because it's switching a high when the TA exceeds Tref. So when TA is greater than Tref, which is on the minus input, you get a 1 on comp. And you can actually zoom into the waveforms as well. If you click on the magnifying glass and zoom in, you can basically select by drawing a box around an area and zoom in a bit closer, and you can see that the comparator output is responding to the fact that the TA is exceeding Tref. There is a slight delay there. If we zoom, the other thing you can do, if you do zoom in, you can zoom out using this button here with the vertical fit and the horizontal fit. So you should be able to escape zooming out and just make sure everything fits on there like that. And that's the comparator output, which feeds into the D-type flip-flop. So the next thing to do is to add the other digital signals. So the clock, the reset bar, and the Q. We'll not bother with QN. If we select all of them and trace them in the transient window, it gives individual waveforms for those. If we run those waveforms, run the simulation again, all the waveforms will be updated, and now we can see the full set of waveforms from the design, and the clock's there, the reset's there, and the output of the flip-flops there, which is kind of just a delayed version of the input. If you go to the zoom mode and you put the cursor in the digital waveform, when you zoom it just creates a straight line and just zooms into that area. So you can see now the Q output of the flip-flop is triggering at the positive edge of the next clock after comp goes high, and that is what we would expect from that. So we zoom out again. So as I say, this is really the Smash simulator is quite good, considering that it's free, and you can also use cursors to make measurements. So for example, if you go to the main toolbar, there's a cursor which, if you move into the waveform and click twice, you can add multiple cursors which you can select and you can drag around, and as you move them around, it gives you the measurements of the waveforms, all the waveforms as you move along, whichever cursor is active. You can also measure things using the measurement mode, which is kind of like a measuring stick, and you can just put the measuring stick anywhere and you can measure to the next peak. For example, it will give you measurements like, for example, if you want to measure peak to peak, you can measure the peak to peak there of 20 volts, or if you want to measure the period, you just measure across to and get the frequency of 1 megahertz and so on. So that's quite useful. Another feature is this magnetize feature, which allows you to follow the value along with a kind of a sticky magnetic point. So if I just click on a waveform, and this little blue dot allows me just to move along a waveform, and I can select any waveform and it'll give me information about that waveform as I move along the waveform and see what's going on in the system. So it's kind of just scraping the surface really of what you can do with this. To stop the magnetization, you have to click on the demagnetize button, and you can do a lot of different things with the software. It's very powerful. It seems to not want to stop magnetizing. Right, these are the data points I mentioned. If you click on the magnetized computed points, it actually shows you where the data points are that it solves when it's running the simulation. You can see them on the waveform for TA quite clearly, and you can see it's doing lots of data points, which means that it's quite an accurate simulation. So I'm going to turn off that now, if I can. It doesn't seem to want to let me to do that, so okay, turn that one off as well, and go back to the pointing. So yeah, so there's a number of things you can do with the design. The data points display, sometimes the display won't update, so you might need to rerun it just to get the display to sort of clean up and go back to its initial state. I can't seem to get rid of the data points for TA, which I should be able to remove. Show points. Yeah, there, that's it. Yeah, there's a lot of things you can do. You can also change the radix of if you have buses, you can select different radices for the digital waveforms. So this simulator can actually just simulate Verilog designs on its own as well as mixed signal designs. So once you finish the simulation, the main thing is to make sure that the PAT file is updated, because this contains this contains all of the transient trace commands. The logic trace commands are all there as well. So that must be updated to, don't save it, it's already saved as a PAT, to allow these settings to show. So what I'm going to do is I'm going to close the design now and then try and reopen it to see if we can get back to this result. So I'm going to close the design. It's File, Close Circuit, or click on the Close Circuit button, and it closes the simulation, and it usually comes up with some little information windows which give you an idea of some of the things you can do with this software. And it also leaves in the recent projects, it shows the pattern file that you last had open. So if you just want to go back to the simulation, you can click on either one of them, and it should just reopen the simulation. And the transient window doesn't appear straight away. It's loaded the circuit. There's the pattern file. If you go to the files, and where it says waveforms transient analysis, double click on that, it opens up the waveform window, and you can see your waveforms have reappeared. And you may want to actually, let's say you wanted to change something. So if I go into the netlist now, and let's say I want to change the value of one of the resistors, the resistor basically sets the value of the threshold in the voltage divider. So I've got 6 volts coming in here, and that 6 volts is divided into Tref over 2 in the waveform. I'm actually looking at Tref rather than Tref over 2, so perhaps we need to add Tref over 2 to the waveforms as well. I'll put that in there. And then I'm going to, like I say, I'm going to change the value of the resistors now. I'm going to change the this resistor to 2 kilo ohms. So I'm going to change R2 to 2 kilo ohms. So just change that to 2 kilo ohms, save the file, close it, and what should happen now is that if I run the simulation, it should automatically recompile the files in order to update the fact that I've changed that resistor. So it will actually do that, hopefully. The message is flashing past that it has actually compiled things, and if we open up the waveform now, I think the reason that Tref over 2 isn't there is that I forgot to save the pattern file before I ran the simulation, so I need to just add that in, and you can see now that Tref over 2 is 4 volts, because it's no longer Tref over 2. Tref is 6 volts, and that means Tref over 2 is now 4 volts. So the yellow line is actually where the comparator is comparing with the TA, and that we zoom in, we can see that if we add a cursor and move that cursor along to where they cross, so there's the crossing point where the TA crosses TREF over 2, the comparator output goes high after a short delay, and it's a delay of about 10 nanoseconds, which we should be able to see that there. It doesn't seem to show the difference between those two, unless it's showing it down here. DX, I think this is just measurements which are from before. But those two cursors are showing the delay for the comparator switching from a 0 to a 1 after you actually go through the threshold. So that one is at 1.066 and this one's at 1.076. So there's your 10 nanoseconds. I'll move this along now to the crossing point where the comparator, the plus input is going below the minus input, and we look at the point at which the comparator switches. It should also be a 10 nanosecond delay, which it pretty much is. If you look, it looks like the same kind of time period. 1.47, 1.4, that's at 1.434, and that's at 1.447. That isn't 10 nanoseconds, but I think I haven't quite got that in the right position. I can zoom in a bit closer and go back to the, so that point where it's crossing is at about 1.434, and this is at 1.446, and the comparator goes low. So it's a difference between 4.6 and 3.4, which is 12, so it's near enough. There is a kind of an approximation with these things because it depends on where the data points are in the simulation. And here you can see that there's quite a lot of data points being used to calculate that sine wave. Even if you go in closer, you can see now these are the actual solution points of the analog waveform. As I move down there, I'll just turn those off now and turn off the magnetize. And this is the zoom out button, remember? Zoom to the full extent of the waveforms, and that's the Smash simulation tool. It's really powerful software, and you can investigate all sorts of mixed signal properties. So once you're finished with that, make sure that you have updated all your files. All these files are saved. You don't need to save that. It does actually just save the file in the PAT file, and then you can just close the file, and that closes the Smash simulator. And that's it. So that's the end of this video, which will be uploaded onto e-learning very soon.